I'd like to welcome everybody to this lesson on parent functions. We'll start by reviewing the objectives for this particular lesson. Um, you're going to find that the learning is going to take place through what you see in the video and also through whatever interactions that we happen to have with one another in the classroom. Okay, so the objectives are to understand and communicate through words, graphs, and symbols the characteristics of parent functions. We're also going to take note of a few other ideas. Before we get into this, I want you to recall that a function is a relation where each element in the domain maps onto exactly one element in the range. For example, if we take y equals the square root of x, we can say that that is a function, yet y equals plus or minus the square root of x. I'm just going to rewrite that so it is actually represented appropriately. Is not, because it fails the VLT. Secondly, a parent function is any function from which more complex functions can be made. So you were doing that in previous years through transformations. We can also achieve new functions through combinations and or what we call compositions. So we should see combinations throughout the course, and we'll look at compositions at a later point in time. Okay, getting a little bit ahead of myself here. Let's begin with some minds on math. Okay, we'll look at some old functions, and we'll talk about their representations. So on the left-hand side, we've got a graph of the linear function g at x, 3x minus 4. Well, if you look at the graph, you can see its properties. Minus 4 is the y-intercept, okay, which we have here, as is indicated in the equation. You can also see that the line does have a slope of 3, okay, as is indicated in the equation. And we can also see that on the graph. So for every increment, for every increase in x of 1 unit, we can also see a corresponding increase of 3 units. Okay, hence the idea of slope. So you're going to notice that your table is blank, and we're going to fill this in. My table, which I have on another slide, has a few screen shades, and we'll reveal these as we go. Okay, so if you look at the left-hand column of the table, we have ordered pairs, x, comma, f at x. Okay, now remember that f at x is also the same as y. Okay, now if we study the ordered pairs 0, 0, 1, comma 1, and 2, comma 2, notice that in every case the x-coordinate is equal to the y-coordinate. So what we can say is that y is the same as x. Y equals x. If we use our function notation, we can say that y equals f at x, which also can now be written as f at x equaling x, given that x and y are equal to one another. What we're going to do is we're going to take a look at the function equation, which we have here, and we're going to identify just exactly what transformations are being made to the parent function of g at x, which is the answer to question number 2. What is being done to y equals x to produce the blue graph, which is also going to produce the ordered pairs that we can see on the graph. So let's have a look at our transformations. What we can say is that the x values are going to remain the same, although we're going to end up tripling the y values, and from that we're going to subtract 4. Okay, so let's see this in action. Okay, so you notice that the x value is 0, the y value is 0, it's being subbed in for f at x, and there's just one small error here. You'll notice that the bracket is in, or that we're missing a bracket in fact. Let's just put one in here. Okay, so we triple 0, subtract 4, and we end up with a y value of -4. So take note that that ordered pair 0, -4 does happen to be on the graph. Same thing applies. We use the transformations that were given to us, so we can map an old point onto a new and transformed point. The y value in this case is 1, so we'll sub that in for f at x. X, of course, was given as 1, and we'll do the calculation and arrive at 1 minus 1. Last but not least, we'll sub in 2 for y. We'll evaluate, and 2 comma 2. So do take note that under the transformations of the graph y equals x, all of these coordinates happen to be on the graph of G. Last but not least, just in a few words, we'll make a statement about what happened to the original graph. To give G at x, we can say that the graph was vertically stretched by a factor of 3, which was then followed by a vertical translation of 4 units down. Okay, so let's look at another old function, one that we've been through before. It appears as though the orientation is off of the smartboard, so having some difficulty switching from slide to slide. Okay, so unfortunately, if you don't mind, what I'm going to do is I'm going to attempt reorienting the smartboard at this time, which is generally not necessary. You might be hearing a few chimes in the background, and that's simply me orienting the board. So let's hope that this works better this time. Let's look at a different function. In this case, the rule, or G, is producing a new function, G at x, as negative x plus 1 all squared plus 2. Okay. Same thing. We'll start off by looking at a set of ordered pairs which are not on the graph we have now. We have 0, 0, minus 1, 1, and minus 2, 4. Okay. You might recognize these coordinates as belonging to a particular parent function for the graph of G. Okay. And that function is none other than y equals x squared. Okay. So what we'll do is, using our function notation, we'll let y be f at x, and so f at x is equal to x squared. Okay. And you can test that idea. You can see that 0 squared is 0, that minus 1 squared gives you 1, and that minus 2 squared would give you 4. So now let's consider the transformations that would be occurring to the graph, to the function f at x equals x squared, in order to produce the graph of G. So what we're going to say is that all of the x-coordinates are going to translate to the left by 1 unit. So do recall sorry about the pause here. Just have someone at the door, which happens during filming every once in a while. But just take note that what's occurring to x is that it's being translated to the left. So the graph moves opposite to the sign that's there by the magnitude of the number that's listed here. Other things that are occurring as well include a reflection in the y-axis, and you can see that here. Of course, f of x is the y value. And lastly, we can also take note that there's a vertical translation of 2 units up. So let's go ahead and apply the transformations to the original elements in the ordered pairs. So the first ordered pair for the graph of G would be minus 1, 2. The second one, if we substitute the original x and y values and evaluating, we'll end up with minus 2, comma 1. And last but not least, by substituting the coordinates negative 2 and 4, we'll produce a new mapping. So minus 2 comma 4 is going to map on to the ordered pair negative 3, negative 2. And of course all of these new ordered pairs do appear on the graph of G, which we have to our left. Lastly, to finish the slide off, we'll make a statement as to what occurred to the graph of F in order to produce G. So we have a reflection through the x-axis, a horizontal shift of 1 unit left, and a vertical translation of 2 units up. So this video is reaching about a 12, almost 13-minute mark. I'm going to pause it here due to time restrictions on what I can post to YouTube. So we'll have a second part to this as well.